Hello, this is Dr. J. Suryanarayana, Associate Professor, Department of Physics, Indian Institute of Technology, Hyderabad. So I'm here to explain you the most important work that we have carried out in our laboratory, which is basically graphene oxide based resistive random access memory device for the neuromorphic computing applications. From the work that we have carried out, we believe that the graphene oxide can be a potential candidate for the neuromorphic computing application. So now the question is, what is the neuromorphic computing? So the neuromorphic computing is the one which mimics the brain inspired computing. So for instance, if you consider the brain will have neurons and two neurons will be connected by a synapse, and we would essentially have 10 power 11 neurons, and these 10 power 11 neurons will be connected by 10 power 15 synapses. Okay, so the connection strength between two neurons can be called as the synaptic weight, and the synaptic weight can be modulated by using time dependent signals. The most essential neural functions for learning process are long-term potentiation, long-term depression, and spike time dependent plasticity. We try to show all these properties using our graphene oxide based resistive random access memory, which may be useful for the future neuromorphic computing applications. So this is the kind of device that we have developed in our laboratory. This is graphene oxide is the active material. The bottom electrode is FTO and the top electrode is silver. And this is the kind of IV characteristics that we have obtained. So as you can see from this picture that analog switching is evident, which is very much essential for the neuromorphic computing. And we also try to show the endurance and retentivity characteristics. The endurance up to more than 400 cycles we could able to get, and the retentivity we could show up to 10 for 4 seconds. And we also try to show multi-level resistive switching using this graphene oxide based resistive random access memory device. As I mentioned, we also try to show the long-term potentiation and long-term depression by applying the continuous pulses of 1.2 volts for the long-term potentiation and the negative 1.2 volts for the long-term depression. What you could see here is that continuous increase in the conductance for the positive pulse voltage and which mimics the long-term potentiation, and the decrease in the conductance for the negative pulse which indicates the long-term depression. On top of that, we also try to show the spike timing dependent plasticity by applying the presynaptic pulse and the postsynaptic pulse. As you could see here from this graph that the conductance increases as the relative timing between two spikes is short. And this paper has been published in nanotechnology along with my student Dr. Dwepak Prasad Sahu. And based on this work, the Times of India also published an article in their newspaper. And we believe that the work that we have carried out is very much important in the direction of the materials perspective, which may be useful for the future neuromorphic computing applications. Thank you very much.